Okay, let's begin. Hello everyone, and welcome to our sixth lecture on virtual lab in chemical engineering. So in today's lecture, we will be performing experiment where we will evaluate the performance characteristic of centrifugal pump. Right. So what I will do first, we will go through the theoretical part of different pumps. What are pumps? Their use, types of pump. Then we will move forward with the centrifugal pump and then discuss the characteristic curves for centrifugal pump and then move forward with the virtual lab experiment part. So let's begin. As I said, aim of our experiment is to conduct test on centrifugal pump to plot the operating characteristics. So when we say operating characteristic of centrifugal pump, what are we referring to? So operating characteristic curves for centrifugal pumps are nothing but the curves for head versus flow rate for centrifugal pump. So this head is total head developed by pump. Then we have power consumption versus flow rate. We have efficiency of centrifugal pump versus flow rate data. So this three curve itself are referred to as characteristic curves for centrifugal pump. So let's dive deep into this. So first, what are the pumps? So pumps are this mechanical device which we use to transfer fluid from one place to another place. So generally it's from lower pressure region to a higher pressure region. We use this mechanical device which draws fluid from a lower pressure region and puts it into the higher pressure region by converting its mechanical energy into the hydraulic energy. So pumps converts their mechanical energy into hydraulic energy, right? And they are widely used in industry, households, infrastructure system, or to transport the fluid efficiently. So in our house also we have generally this water pumps which we use to fill up our overhead tanks, right? You might have seen in your apartment also. So there are this water pumps which are submerged inside your bottom tank, ground tank, or sometimes they are non-submerged kind of pumps also. Okay, so the application of pumps, so they are widely used in industry for a water supply, oil and gas industry to transfer oil from one place to another place, in chemical processing to handle various corrosive fluids, right? So we have previously discussed the flow of fluid in this pipe network where we use these pumps to transport fluid in this pipe network. In that experiments, we computed the pressure drop generated in these pipes, which we had then which we will require to design the pump capacity, right? So we will come to that also, what is the pump capacity, design capacity and stuff. But pumps are needed to transfer fluid from one place to another place. Similarly, wastewater treatment plant also pumps are needed. Another application is in medical devices. So blood pumps in dialysis machine. Even in the automotive, when we have this fuel pump or coolant pump, they are also widely used. So pumps are everywhere. It's not just pertaining to the chemical industry, but rather from day-to-day application to even medical applications also. Okay. So if we talk about types of pumps, so pumps are categorized based on their working principle. So we have two major categories. One is rotor dynamic or dynamic pump, and another is positive displacement pump. So positive displacement pump, as the name suggests, they work on a principle of fluid displacement, right? So this pumps moves fluid by trapping a fixed amount and forcing it to discharge pipe. Okay, so the common example that you have heard will be a piston or plunger type pump. So where we have this piston type system. So this is how it will look like. That fluid will come here there are generally NRV valves, non-return valves, present in the suction and the discharge head. So because once the plunger will move this side, suction will be created here, fluid will come inside, then NRV valves will be closed, plunger will move again to inside, and then fluid will flow. So this way the fixed amount or fixed volume of a fluid is displaced. So that's why these are positive displacement pump. Then we have another type, instead of piston, if you have a plunger, then it's a plunger pump. Then we have diaphragm pump also. Another type of positive displacement pump, where instead of this reciprocating motion, we use rotary movement. So they are this gear, screw or vane pump. So if you remember the gear type flow meters, where the flow rate was calculated based on the fixed volume that was being displaced in the flow meter, right? So similarly, like the gear pump also works on the same mechanism, where you have sorry, this is not a very good drawing, let me change it. So let's consider globe type gear, the example that we had studied previously. So this sort of a pump, where the fixed volume is displayed by the rotation of our gears or screws, right? So this is a positive displacement. This is also kind of a positive displacement pump, where fixed volume of the fluid is displaced from one place to another place. Then the dynamic pump, they uses the principle where the rotational energy or kinetic energy is converted into the pressure energy. So first is centrifugal pump, which is the most common type of rotodynamic pump. Then we have axial pump. So difference between centrifugal pump and axial pump is based on the direction of the flow. So in the centrifugal pump, fluid is moving in the centrifugal direction and then going outside, while the axial pump, as its name suggests, fluid is moving parallelly to the axis. Right? Then we have combination of both centrifugal and axial, which are referred to as mixed flow pump, which are combination of the both. So this is another visual representation of pump classification. So you can see the main classification are positive displacement and the dynamic pump, and then further classifications can be provided. There are this special effect pumps also, which use this concept of electromagnetism or jet to convert kinetic energy into the pressure energy. Now each category has its own advantage and use case. So centrifugal pump gives you generally higher flow rate. They have a simple design, but they are sensitive to higher viscous fluid, right? So in that case, we will go to the reciprocating pump. So reciprocating pump it has a pulsating flow, although they are high maintenance, but they can be used for, so this is not a disadvantage, rather a use case. So they can be used for high viscous fluid, because the movement of fluid is done via this positive displacement in the reciprocating pump, right? So they are generally used for the higher viscous fluid, so high pressure self-priming. Similarly, rotary pumps also, which handles a viscous fluid, there are no pulsations, but rotary pumps are slightly expensive. So where you will find the all the applications which involves small amount of fluid oil injection, you will find the rotary pump. Centrifugal pump are most common for a higher flow rate, but if you want much higher pressure, then the reciprocating pumps are recommended. So this is the diagram of centrifugal pump. As we said, that there is this suction inlet. Fluid will come here, then it will go out in the discharge. The motor here, the pump is connected to motor. Motor is connected by a shaft to an impeller which rotates and converts fluid, increases the kinetic energy of the fluid. So our fluid will rotate inside the casing and then will go out from the discharge. The output throat area of the discharge is small, which converts kinetic energy of fluid into the pressure energy. Thus we get the higher pressure value and in the discharge side, right? So fluid enters axially, accelerates radially and exits through the volute casing. Volute casing is this pump casing, which increases the pressure area, right? So main component of pump includes impeller. So impellers are this rotating part. So there are different types of impellers which are used to convert mechanical energy into the kinetic energy to the fluid, to give the fluid kinetic energy, right? So depending upon type of fluid that we use, we might have open, semi-open or closed impeller. So I will show you the graphical representation of this impeller also. Then this is the casing. Shaft and bearing are, casing is this one, right? Shaft and bearing are to connect the motor and the rotor. Then there are seals to avoid any leakage. Then suction and discharge nozzle, right? So this is the basic layout of centrifugal pump. Now when we say this characteristic of the centrifugal pump, so characteristic, as I said previously, that it refers to the relationship between the key performance parameters. So what are these parameters? So it's head, flow rate, power and the efficiency. So generally the head, power and the efficiency, these three are plotted against the flow rate. So as you can see in this diagram, we have head versus flow rate, we have power versus flow rate, and then efficiency versus flow rate. So we have this three plots already ready. Right. So when we have a low flow condition, in that case we have the highest head while the power requirement is minimum. So generally this point is referred to as no discharge point. So when we start the centrifugal pump, so it's generally started by closing the outlet of the discharge valve. So there is no flow, but the pressure head is created inside your system, which is generally done to avoid the tripping of the pump due to the generation of higher flow rate inside your pump. Okay, so generally pump, when centrifugal pump, when it is started on the closed discharge. So for the closed discharge, when we have zero flow rate, the corresponding head is maximum. Corresponding head is maximum and power is minimum. As soon as we increase the flow rate, we open the outlet of the discharge, the power requirement of pump will rise. So pump power requirement will increase. With that, the head developed by the pump, total head developed by the pump will go down. And if we compute the efficiency of pump, so we will get this sort of a curve. So I'm not going into the equation part of the efficiency of pump and head calculations. So you might have read it in your fluid flow operation subject. So for the purpose of this class, I am not pertaining to that details as of now, right? So this is how this efficiency curve looks like, and a point where you get the maximum efficiency, which is maximum efficiency is referred to as break-even point. So corresponding head, so corresponding flow rate where the maximum efficiency is achieved is referred to as break-even point, BEP. Okay, so if you want to operate the pump with a maximum efficiency, maximum utilization, we should work somewhere around the break-even point, since we have the highest efficiency near the break-even point. So these characteristics are very useful to decide the use case of any pump. So we should know at what flow rate we can operate the pump, where we can get the maximum efficiency, what will be the power requirement for a pump. So in this experiment, what we will do, we will perform an experiment on centrifugal pump. We will run pump at various conditions and find its head developed flow, compute the flow rate, and compute the power requirement of the pump. Now here there is one more thing which we can look at. So let's say this is the centrifugal pump, this is the center portion, and this is the point of discharge. Pump is taking suction. So let's say discharge at some elevation Z D, suction is at some elevation Zs. So pump has to lift the fluid from Zs and discharge it to Zd, right? So head elevation that pump has to gain is generally given as Zd minus Zs. Delta Z is equal to Zd minus Zs. Now what all things we will need? See, flow rate we can compute. Here we want to compute all these three quantities. So flow rate can be computed based on with the help of the flow meters, right? So this thing is covered. Head we want to compute the power requirement. So power requirement can be computed from finding the power of input power of a motor that we are using. So what is the power given to run a pump? Okay, so that will give us the input power. So from we can correlate it to the brake horsepower. Then for the efficiency we will require the actual power or the hydraulic power. So efficiency will be given as not this, this is like input power or actual power, you can refer it that way. So that is in denominator, and in the numerator we have hydraulic power, which is the power required to generate the given head, right? So difference of this will give you the efficiency. So input power we can compute from the wattmeter readings, while the to compute the efficiency we have to find the hydraulic power, and there are relations to find that also. For head calculation, total discharge head is given as discharge head minus suction head plus delta Z, which is the elevation difference between height difference between suction and discharge, plus if there are friction losses. Here in the discharge head or the discharge and the suction head is a combination of pressure head plus velocity head, right? So both are the combination of pressure head and the velocity head. The elevation gain is denoted by delta z, and then are the friction losses counted. So this total discharge head H, we can compute it by knowing the condition of our suction and discharge. So this went away. Shouldn't happen. So as I was saying, this is suction. Consider it at the elevation ZS. So we know we can compute the delta Z. Let's for now consider that there are no friction loss. So this can be neglected, right? Generally velocity heads, this are also neglected since the pressure head values is much larger than the velocity head, right? So we have to know to compute the discharge and suction head, we will need to know the pressure at suction and the pressure at discharge. Once we know this, we can convert it into the pressure head value by dividing it to rho g. Then the total discharge head can be considered as discharge head minus suction head plus elevation gain plus friction losses. So this total discharge head suggests us that pump has to develop this much of head to deliver the fluid. Pump has to develop this much pressure to deliver the fluid at a given flow rate at given discharge condition P discharge, right? So we computed the discharge. Let's say once you know the discharge, now we know the total discharge head, okay, we know the TDH, then we can compute the power requirement as the pressure that we have to generate. So that is H rho mg into the flow rate at which we want to compute at flow rate which we want to develop this head, right? So here the H is total discharge head, Q is flow rate of the pump, and this is total power, right? But this power is ideal, does not account any losses, right? So this we can refer to as P ideal or P hydraulic, okay. So this is the power required considering there are no losses, everything has 100% efficiency, pump, motor, there are no friction losses. But in actuality, power consumption, P actual, or you can refer it as P input, is greater than the P hydraulic. Thus the ratio of these two can give us the efficiency of pump, which is P hydraulic divided by P actual. So these are the two calculations that we have to do in our experiment, and once that is done, we can draw the characteristic curves for the pump, right? So this was the theoretical part. Now let's move with the virtual lab experiment part here. So if we will see in the course content, go to the performance characteristic of centrifugal pump. So there is some basic theory given for the centrifugal pump. I have not gone into this theory much because I assume that since the pumps are very basic concept, you must have read it in your fluid flow operation, right? So these are the types of impellers which I was talking about. So depending upon our fluid application, the type of fluid that we use, we can select either of these impellers. These are the calculation part. So as I was saying that input power can be computed from wattmeter reading. So there is equation given for that to convert accounting the motor efficiency to compute the actual input power. Output power, or rather the ideal power that we need, is the head that should be developed by the pump at a given flow rate. So it's H rho g into the Q. Then the efficiency is the ratio of this to power, which is hydraulic power divided by the actual power into 100, right? And the total discharge head can be computed by here a difference of discharge head minus suction head plus elevation gain. So here friction losses are not accounted. One issue here in this virtual lab is that they are taking the summation of discharge and the suction head, but this is wrong, as we had discussed that this total discharge head is discharge head minus suction head plus elevation gain plus friction losses, right? So there will be a minus sign here. Oh, I forgot to share screen here. Sorry. So as I was saying that the theoretical part is given here, type of the impellers. These are the equations for output power. So output power, they are referring it as output power, but it's in the hydraulic power required for the pump to generate given head at a given flow rate, right? Then the input power can be computed from the wattmeter reading of our motor, and there are this efficiency of motor is also accounted to compute the actual power. So that part is also done. Then the efficiency can be computed from pump efficiency. So this efficiency is pump efficiency, which is the actual power, output power, or the hydraulic power divided by the input power. I was saying this, that the head calculation, so here it should be total head is HD minus HS plus delta Z, right? So that should be a negative sign. So I think they have made some sort of error here, because same error has been seen in their calculation part also, in the simulation part also. So before going to the simulation, let's first refer to the actual experimental setup. How does it look like?
Centrifugal pump. This is the experimental setup. The objective of this experiment is to conduct performance test of centrifugal pump and to plot the operating characteristics. Switch on the power to start the pump. Rotate the handle and set the speed of the motor to be constant. Measure the speed of pump using a tachometer and record the value. Note the initial reading on the hook gauge. Open the delivery valve and allow the water to flow in the channel. Using the hook gauge, get the final reading for V notch.
In the last lecture we studied about the V notch and the rectangular notch, right? So there, based on the change in the height of the water level, we can compute the flow rate of our fluid, right, in the open channel. So here, to compute the flow rate, the V notch setup is used, and you can see these are the calculation part to compute the actual flow rate from the height of the crest, from the height of the nap over the crest.
Note the delivery pressure reading corresponding to the discharge. Take this.
So here the mistake that I think is that as
Note the
generally the discharge pressure of the pump is greater than the input pressure or the suction pressure. So you can see here the discharge pressure value is somewhere around 0.67 kg per centimeter square, right? But they are referring to as, so they have given this reference value of 0.1, which is anyway okay, that might be some different value.
delivery pressure reading corresponding to the discharge.
Corresponding suction head should be less than the discharge pressure value. So that is generally the objective of the pump, right? That you want to pump out the fluid from a lower pressure to the higher pressure. So here they have given suction head value as 0.48, while the discharge was at 0.1, which is not generally the case. So if the discharge is at higher pressure compared to the pump itself, if the suction is at the higher, if the suction is at the higher pressure compared to the discharge, then we don't need a pump, right? Fluid will flow from the high pressure region to the lower pressure region regardless of the pump. So this is the issue which I find this setup has. It could be that the video that they have made or the simulator that they have done, there is some miscalculation that they have put. So here also you can see the suction pressure. So this is the suction pressure, that is somewhere around 0.32, okay, while the discharge pressure was at 0.7 or 0.8 kg per centimeter square.
Head pressure reading corresponding to the discharge. Calculate the total head. Note.
So based on these pressure values, we can compute the total head. So that thing is done. Now to compute the actual power requirement,
The wattmeter reading corresponding to the discharge. Calculate the input.
Wattmeter reading of the motor are computed. So we know the wattmeter reading, we know the actual discharge, we have the total head. Then we can compute the input power, right? So wattmeter reading is used to compute the input power or the actual power. Output power or the hydraulic head required for pump to generate this amount of flow rate is computed based on the H rho g into total flow rate value, and the efficiency is computed. So this is how this experiment follows. Now the issue, as I discussed, that the pressure calculations that they are doing for the total head, there should be difference between the H total will be HD minus HS, and generally discharge is at the higher pressure, so this should not happen. So I'm not sure why this kind of thing they have done, but be cautious when you are referring to this VLab, that there is difference in the calculation of total head, and there is an error in the suction and the discharge pressure value, right? So basically here I am not focusing on to this part much, because overall idea is for you to understand how this experiment is being performed, and to gain the understanding of the experiment and what we are learning here, right? So this is the diagram for our experimental setup. that water is drawn from this well. It is going into our centrifugal pump. So there is this pressure gauge at the suction, pressure gauge provided at the outlet, discharge, right? There is this valve which is connected to discharge. So initially pump is started where discharge valve is completely closed. Then you gradually open the discharge valve. This flow will go into the open channel. Here the Venturi, the V0 setup is used to compute the total flow rate from the pump, right? Wattmeter is connected to find the power consumption of our motor. So the experiment begins. You start the pump. Adjust the speed of the motor. You can use the technometer to note down the RPM of your motor also. Open the discharge valve. Take the height of water level above crest for V0. So first we took a height till the crest, then increase the flow rate, compute the height, new height. So this is the difference, and the actual flow rate is given by this equation. So this equation we had derived, right? For V0, flow rate is proportional to the h to the power 2.5, and if we account coefficient of discharge as 0.6 and simplify the whole equation, which is 8 by 15 under root 2 g into cd, you will get the value of somewhere around 14.17 by considering the cd as a 0.6. So once we have this, we can compute the actual flow rate. So let me calculate that. Here. So 14.02 raised to the power 5 by 2 into our constant is 14.17. So the value that we are getting is 10428.93, this much centimeter cube. There are some question and answers. So head of water is calculated by final hook gauge reading minus initial hook gauge reading, right? Now note down the delivery head pressure. So this is coming as 0.1. Note down the suction head pressure. So here they are giving it the value of 0.48, which shows that suction is at the higher pressure value, but this is not the case. If the suction is at the higher pressure value, then we don't need a pump for a fluid to flow. It will flow from high pressure to low pressure itself, right? So this is wrong. So this is where they are making a mistake, and they are computing total head as a summation of discharge plus suction plus Z. So this Z is the difference between height difference between suction and discharge, so which is around 43 centimeters. So this looks fine, but the total head calculation, total discharge head, it should not be HD plus HS, it should be HD minus HS plus Z, where HD should be higher than HS. Generally it is higher than the HS, right? But here it's wrong. So here they are doing the summation which is not correct. So it's like 4.8 plus 1 plus 0.43, so 6.23. But this is not correct, you have to take actual difference, right? So remember, this is HD minus HS plus Z, and the suction value will be obviously lower than the suction head, will be lower than the discharge head. So we computed this. Now note down the wattmeter reading for the given flow rate for our motor, right? So that reading is noted. Now first let's compute the input power. Input power is actual power that we supply, so it is given as wattmeter reading into WC Nm into Np. So this are nothing but the constant to compute the actual power by considering the efficiency of motor, the phase supplied, power phase supplied to the motor, right? So 2 into 3 into 0.8 into 425. So 2050 is the actual. Did I make many mistake? Oh sorry, 2040. Yeah, sorry. 2040, this is the actual power supplied to a pump via motor. Then the output power, so this is not actually output power, rather we should refer this as the ideal power required to generate this much flow rate, right? So it's Y into Q actual into H. So this Y constant is given as specific gravity, so that is nothing but G into density of water, right? So this is that rho G parameter. So if you will multiply this with the head is 6.23. remember, this head is exactly not correct, but right now we are going with their formula and convert it to the SI unit. Then you will get the power as 637.375. Okay. So this much flow. So our efficiency will be the difference of actual powered ideal power required divided by the actual power. So this is coming somewhere around 31.245, right? So this value is correct. So this much is the efficiency for pump at a given flow rate. Now again we have to change the flow rate and do the calculations. So what I will do, I will skip through this step. I won't be putting this calculated value again. You can do it on your own also, but we want to generate the characteristics. So for that, what we have to do, we have to run the pump at various discharge flow rate, and the compute the corresponding power, head and the flow rate. Flow rate is already known. Compute the corresponding power, efficiency and the head, and at the end we will plot all three. So I'm just putting a random value to check. Tool used to measure the pressure, it's manometer, correct? Note down the wattmeter reading, do the next calculation. Right. So this time efficiency came as 35. Again change flow rate, measure the pump efficiency at different other flow rate. Putting arbitrary value. wattmeter constant, I think it was 2 watt. Yeah. So you got the result here. After this 3 trial, I mean, in ideally you have to do multiple readings at different flow rate. Once you do that and you have sufficient data, then you can plot this characteristic curve. So first let's look at the total head versus actual discharge. So initially head will be the highest. At the lower flow rate we will be able to generate the highest pressure in the discharge, and then as flow rate increases the discharge value will go down, discharge pressure will go down, right? So this was the H versus Q curve. Then the ideal power, so here they are referring it as output power versus actual discharge. So since it follows the actual equation, it's an ideal power, so it follows this efficiency curve, but the actual power will be constantly increasing with the flow rate. Okay, so we refer to generally this actual power, right? So this is because of the addition of losses at the higher flow rate. Then you have the efficiency versus discharge. So it should be low at the lower flow rate. At some point in between we will get the maximum efficiency, which corresponds to break even point, and then after that again for the higher flow rate the efficiency will go down, right? So these are the characteristic curves. So for each type of centrifugal pump, these characteristic curves are given by the manufacturer itself, so that we can decide at what point we should operate our pump based on our requirement and what will be the power consumption at desired conditions, right? So this was the test, this was the virtual lab experimental part today. In the theory this time I haven't dived too much into the basics of pump, because since it's a very vast topic, so I haven't touched too much of it. You will find so many resources for the pump. There are some details that you can look for, what is the NPSH of pump, what are the cavitation conditions for the pump, how to prevent the cavitation in centrifugal pump, etc., right? But do remember here that the calculation of the total head, this equation is wrong. It should be HT minus HS plus Z plus delta Z and some losses if you are encountering it. Okay, so just be precautious. I will try to contact the virtual lab here to clarify this part, but till then when you are doing it, when you are testing this virtual lab, keep this thing in mind, right? So with that I will end today's lecture. If you have any doubt then we can discuss it afterwards.